The universe is filled with structures that defy belief. This is a journey through these giants of the cosmos, from record-breaking stars and black holes to structures so large they challenge our understanding of the universe itself. We'll explore how astronomers measure the unmeasurable and what these colossal shapes might tell us about the universe's past and its future. Get ready to feel insignificant in the best possible way. Red supergiant titans, the case of Stephenson, 2:18. Among the grand wonders of our universe, there exists a category of stars so massive and so vast that even the distances we commonly use in astronomy seem to fall short. These are the red supergiants, enormous bloated stars in the late stages of their lives, quietly preparing for an end that will be as explosive as their lives were expansive. Among these titans, one star stands out for its sheer scale: Stephenson 2:18. Stephenson 2:18 is, by current estimates, a candidate for the title of the largest star known by radius. Take the Sun, something already unimaginably vast to us, and then imagine something 1,000 times wider. If Stephenson 2:18 were to replace our Sun at the center of the solar system, it would engulf Mercury, Venus, Earth, Mars, and stretch all the way past the orbit of Jupiter. Located roughly 19,500 light-years away from Earth, Stephenson 2:18 lies in a dense cluster of red supergiants known as the Stephenson 2 cluster. This is a star-forming region buried deep in the dust of our galaxy's plane, making it difficult to observe in visible light. Instead, astronomers rely on infrared and radio observations to peer through the thick curtains of cosmic dust. What they've found there is a kind of stellar retirement home, where some of the biggest stars in the galaxy spend their final chapters. Stephenson 2:18 is a cool star, in astronomical terms, with a surface temperature of around 3,200 degrees Celsius. That's significantly cooler than the Sun's surface temperature of about 5,500 degrees Celsius. This lower temperature is one of the reasons for its red appearance, a defining trait of red supergiants. Its mass, while still enormous, is not the largest among stars. Estimates suggest it's somewhere around 30 to 50 times the mass of the Sun. But it's the star's swollen outer layers, puffed up like a balloon nearing its limit, that give it such an extraordinary radius. This expanded atmosphere is so tenuous that the outer edges of the star are barely bound to the core, more like a thick fog than a solid surface. If you could somehow stand at the edge of Stephenson 2:18, you might not even realize you were on it. It is that diffuse. While small stars like our Sun can live for billions of years, red supergiants burn through their fuel in just a few million. That's because their massive size demands enormous amounts of energy, and they fuse heavier and heavier elements in their cores in a desperate bid to fight against gravitational collapse. For Stephenson 2:18, this process is nearing its end. As it fuses heavier elements like silicon and sulfur, the time it has left ticks down rapidly. Eventually, when it begins fusing iron in its core, the balance is broken, gravity wins, and the star collapses in on itself. What follows is a supernova, one of the most powerful events in the universe. For a moment, Stephenson 2:18 will shine brighter than entire galaxies, releasing more energy in a few weeks than our Sun will emit in its entire lifetime. What comes after is harder to predict. Some red supergiants leave behind neutron stars, ultra-dense remnants the size of a city, packed with more mass than our Sun. Others collapse further, becoming black holes. Given its mass, Stephenson 2:18 might go down the latter route, quietly warping the space around it, becoming invisible except through the gravity it exerts on nearby objects. But for now, Stephenson 2:18 still burns. Its vast envelope pulses with convection, sending giant waves of hot plasma rolling across its surface. These movements can create massive star spots, cooler regions like sunspots, but on a scale that dwarfs our entire planet. It sheds mass through strong stellar winds, casting off its outer layers into the interstellar medium. This material will one day enrich the galaxy with heavy elements: carbon, oxygen, and other building blocks of planets and life. Despite its distance and the dust that obscures it, Stephenson 2.18 has become a focal point for astronomers studying the final stages of stellar evolution. Because it is so large and luminous, it can serve as a kind of laboratory, helping scientists test theories that are hard to observe in other. Its light, though already thousands of years old by the time it reaches us, tells the story of a brief but powerful existence, of the births, lives, and deaths of stars like this one, which exploded long ago and seeded the cosmos with the materials that now make up planets, oceans, and us. Hypergiant heavyweight VY Canis Majoris, situated approximately 3,900 light-years away in the constellation Canis Major, VY Canis Majoris is possibly the largest known in the universe, standing out even among other supergiants. VY Canis Majoris belongs to a rare and spectacular category of stars known as hypergiants. These stars are much larger and far more unstable than regular supergiants, undergoing dramatic changes as they evolve. It is estimated to have a diameter nearly 1,500 times greater than our Sun. If it were placed at the center of our solar system, its outer edges would start to approach the orbit of Saturn. Hypergiants like VY Canis Majoris burn through their nuclear fuel at an astonishing rate, and the star has already entered the late stages of its life. It has expanded into an unstable, bloated state, shedding its outer layers as it nears the end of its existence. This ever-changing nebula around VY Canis Majoris is a visible testament to the chaotic processes happening inside the star as it consumes its remaining fuel. Despite its cooler temperature than our star, VY Canis Majoris is still incredibly luminous, radiating about 200,000 times more light than the Sun. While much of its light is scattered or blocked by the surrounding dust and gas, it remains one of the most luminous stars of its kind. As VY Canis Majoris continues to lose mass, its future is rapidly approaching. The most likely outcome is a core collapse, which would trigger a supernova. However, there is an alternative possibility. For the most massive stars, the force of gravity can be so intense that the star might collapse directly into a black hole, bypassing the traditional supernova explosion. This phenomenon occurs when the star's core implodes inward without a visible outward explosion, due to its massive gravity overwhelming the internal pressure. Like other hypergiants, it displays highly irregular patterns of mass loss and surface activity. These stars experience massive convective cells, regions where hot gas rises and cooler gas sinks, which are much larger and more turbulent than those in smaller stars. In VY Canis Majoris, these convective cells drive localized eruptions, causing large amounts of material to be expelled into space. These eruptions likely contribute to the formation of the dense nebula surrounding the star and the complex molecules found in the star's outflows. The material ejected by the star provides fertile ground for chemical reactions. Using advanced radio telescopes, astronomers have detected water vapor and carbon-based compounds in the surrounding nebula. These findings highlight the significant role dying stars like VY Canis Majoris play in the enrichment of the cosmos. Recent advances in astronomical imaging and spectroscopy have allowed scientists to observe the intricate details of VY Canis Majoris in ways that were once impossible. High-resolution images have revealed the asymmetric structure of the material being ejected, suggesting that the star's mass loss is not uniform. This irregular shedding of material likely reflects internal processes such as stellar rotation and the influence of magnetic fields, which may be shaping the way the star loses its outer layers. Every new observation reveals more about the violent and fascinating processes that drive the evolution of hypergiants. Supermassive black holes, scaling laws, and galactic bulge relations. Deep inside nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These black holes are millions, sometimes even billions, of times more massive than our Sun. For many years, they were seen as isolated monsters, sitting quietly in the centers of galaxies. But over time, astronomers began to notice something surprising. These black holes aren't just sitting there by chance. Their mass appears to be directly tied to the galaxies around them. It starts with a simple but powerful idea. If you measure the mass of a supermassive black hole at the center of a galaxy, and then measure the mass or brightness of the galaxy's bulge, the dense central region filled with older stars, you find a pattern. Bigger bulges tend to host bigger black holes. This relationship isn't perfect, but it's tight enough that astronomers believe the two are somehow linked. It's called the black hole bulge mass relation, and it suggests that galaxies and their central black holes grow together over time. This idea changed the way scientists think about black holes. Rather than being just a side effect of galaxy formation, supermassive black holes might play an active role in shaping galaxies. It's a two-way connection. The galaxy feeds the black hole, and the black hole, in turn, can affect the galaxy's future. The question is, how? A black hole is tiny compared to its host galaxy. Even a black hole as massive as 1 billion suns is still just a dot compared to a galaxy that might span over 100,000 light-years. Yet somehow, these tiny regions at the center can influence stars, gas, and even how new stars form across vast distances. The key may lie in something called feedback. When gas falls into a black hole, it doesn't just disappear quietly. As it spirals inward, the gas heats up, creating a bright, hot disk. This process releases an enormous amount of energy, sometimes in the form of light, other times as jets of particles traveling near the speed of light. This energy can push against the gas in the galaxy, heating it or blowing it away entirely. If the gas is too hot or too scattered, it can't collapse to form new stars. So the black hole, though small, can act like a switch, shutting off star formation in the galaxy around it. This idea helps explain some of the biggest mysteries in galaxy evolution. For example, why do some galaxies stop making new stars? Why do some massive galaxies appear dead, filled with only old stars and no signs of new ones? One answer may be that their central black holes grew so large and active that they heated or removed the gas needed for star birth. Observations of hundreds of galaxies show that the mass of the central black hole almost always falls within a predictable range, based on the size and properties of the host galaxy. This connection holds true across different types of galaxies, and even in galaxies that are billions of light-years away. One of the earliest clues came from studies of nearby galaxies using powerful telescopes like the Hubble Space Telescope and large ground-based observatories. By carefully watching how stars move near the galactic center, scientists can infer the presence of a massive object, something too small to be a cluster of stars, but too heavy to be anything else but a black hole. The faster the stars move, the heavier the central mass must be. And again, those masses lined up with the mass of the surrounding bulge. It's not just the stars that give away the presence of a black hole. Gas clouds also respond to the black hole's gravity, often forming swirling disks or emitting strong radiation as they fall inward. In more distant galaxies, especially those in the early universe, these processes light up the galactic core, making the black hole visible as a quasar, a kind of cosmic beacon powered by a hungry black hole devouring matter. Quasars were once thought to be rare, but now astronomers understand that they were common in the early universe. Many young galaxies went through a quasar phase, suggesting that black hole growth was an essential part of galaxy evolution. Over time, the quasar quieted down, the black hole settled into a less active state, and the galaxy matured. Elliptical galaxies, which tend to have large, round bulges, often host the most massive black holes. In contrast, spiral galaxies like our own, where the bulge is smaller and the outer parts are filled with young stars, tend to have smaller black holes. The exact mechanisms behind this growth are still being investigated. Some of it happens through mergers, when two galaxies collide and their central black holes eventually join together. Others may involve slow feeding, where gas from the galaxy's core slowly spirals inward over millions of years. The Milky Way offers a quiet example. At its center is Sagittarius A*, a supermassive black hole with a mass of about 4 million suns. That may sound enormous, But compared to the bulge of the Milky Way, it fits the pattern almost perfectly. It's currently quiet, not actively feeding, and invisible to the naked eye. But we know it's there because we can track the orbits of stars near it, especially one called S2, which moves so fast around Sagittarius A** that its path can only be explained by a hidden mass at the center. With the James Webb Space Telescope, or JWST, and future space observatories, researchers are now able to look deeper into the universe's past, watching the earliest galaxies take shape and trying to see when the first supermassive black holes appeared. In these early times, galaxies were smaller, messier, and more chaotic. Yet even then, many of them already had massive black holes in their centers. Somehow, in the chaos of the young universe, the same connection we see today was already forming. Astronomers continue to look for exceptions to the rule, galaxies where the black hole doesn't match the bulge, or vice versa. A few have been found, especially in galaxies that had unusual growth histories or recent mergers. But overall, the pattern holds. Confirmation by quasars, Ton 618 and the heaviest known SMBH. Far beyond the Milky Way, deep in the direction of the constellation Canes Venatici, there is a point of light so distant that it took over 10 billion years for its glow to reach us. That light comes from a quasar called Ton 618. Through the lens of a telescope, it might look like a star, but it is not. It is the visible sign of something far more powerful and far more massive than anything in our galaxy. At the heart of Ton 618 lies a supermassive black hole that is one of the heaviest ones ever measured. A black hole with a mass over 40 billion times that of the Sun. Ton 618 is a quasar, making it one of the brightest objects in the universe. Quasars shine so intensely that they can outshine all the stars in their host galaxies combined. Their brightness doesn't come from the black hole itself, but from the ring of gas and dust that surrounds it. As this material falls inward, it forms an accretion disk. Friction and gravity heat the gas to millions of degrees, causing it to glow with blinding light that can be seen across the cosmos. When astronomers first discovered Ton 618 in the 1950s, it was catalogued as a blue star. It wasn't until the 1970s, after better data had been collected, that scientists realized it was a quasar, and not just any quasar, but one of the most extreme ever found. Its light had been stretched by cosmic expansion, showing that it was incredibly far away. The redshift of Ton 618 is 2.2, meaning the light we see now left the quasar more than 10 billion years ago, when the universe was less than a quarter of its current age. Even at such a distance, the brightness of Ton 618 is staggering. For it to appear that bright from Earth, the black hole at its center must be consuming an enormous amount of matter. Using models of how light is produced in quasars and how black holes interact with their surrounding disks, astronomers were able to estimate the mass of the black hole. Our Sun is a massive object in its own right and could fit 1.3 million Earths inside, while Sagittarius A* is about 4 million times more massive than it. But Ton 618's black hole is more than 10,000 times heavier than that. If you placed it in the center of our solar system, its event horizon, the point of no return, would stretch beyond the orbit of Pluto. The entire solar system could vanish inside it, and there would still be room to spare. Ton 618 shows that even in those ancient times, just a few billion years after the Big Bang, the universe had already produced black holes of unimaginable size. How did something that massive form so quickly? The usual process of black hole growth, starting from a massive star, feeding slowly over billions of years, doesn't seem fast enough to explain Ton 618. So, scientists have begun to explore other possibilities. One idea is that these black holes started with a head start. Instead of forming from normal stars, some early black holes may have come from the direct collapse of giant clouds of gas. These clouds, under the right conditions, could collapse directly into black holes weighing tens of thousands of solar masses. From there, these seed black holes could grow rapidly, feeding on the dense gas around them and merging with other black holes along the way. Another possibility is that the early universe was simply more crowded and chaotic. Galaxies were smaller, but they were colliding and merging all the time. These mergers would have brought in more gas to feed the black holes, as well as other black holes to combine with. It was a time when supermassive black holes could grow faster than they can today. The mass of Ton 618's black hole also fits into the scaling laws discussed earlier. Though its host galaxy is too far away to see clearly, the sheer size of the black hole suggests that the galaxy itself must have been enormous, likely one of the most massive galaxies in the early universe. Ton 618 may be an extreme case, but it follows the same rule. Observations like this one help anchor the theories. Without real examples, scaling laws are just educated guesses. But Ton 618 provides a solid data point at the far end of the scale. It proves that such massive black holes not only exist, but were already in place billions of years ago. And it tells astronomers that any theory of black hole and galaxy evolution must be able to explain how something like Ton 618 came to be. The light from Ton 618 has been traveling through space for more than double the time that the Sun has existed. It passed by galaxies forming, stars exploding, and clusters growing. All the while, the black hole that powers it has likely kept feeding and growing. Whether it is still active today, we cannot know. The light we see now is ancient history. What we can be sure of is that Ton 618's black hole has become a kind of benchmark for extreme black holes, forcing astronomers to rethink how fast black holes can grow, how early they can form, and what that means for the galaxies they inhabit. Hyperluminous quasars, probing the upper limits of black hole growth. Hyperluminous quasars are the brightest quasars of all. What makes them different isn't just their size. It's the way they grow, feed, and burn through the material around them. They're not only heavy, their feeding process is more intense than usual. These black holes are swallowing so much material and doing it so quickly that their accretion disks shine brighter than anything else in the known universe. The energy output can reach up to 1,000 times the brightness of the Milky Way. And yet, all of that light comes from a region smaller than our solar system. Astronomers believe these black holes are growing close to what's called the Eddington limit. This is the balance point where the outward pressure of radiation from the accretion disk pushes back against the inward pull of gravity. If a black hole tries to feed too fast, the energy being released will blow the infalling gas away, preventing more from falling in. It's like trying to pour water into a funnel faster than it can drain. The excess spills out. For black holes, the Eddington limit sets a natural speed limit on how fast they can grow. But some hyperluminous quasars appear to break this rule. Their brightness suggests that they may be accreting at, or even above, this theoretical limit. This is known as super-Eddington accretion. While it was once thought impossible, new observations and computer models suggest it might happen under certain conditions. If the gas falls in from all directions, or if it forms dense, clumpy streams rather than smooth disks, the black hole might be able to pull in more material than expected, at least for a short time. One of the key clues comes from the way hyperluminous quasars appear in different wavelengths of light. Some of them emit strong X-rays, while others seem oddly quiet in the X-ray range. This difference may be related to how thick or chaotic their accretion disks are. In the most extreme cases, the inner regions of the disk might be hidden behind thick clouds of gas and dust, shielding the high-energy light. This suggests that the feeding process is messy and unstable, more like a storm than a steady flow. These extreme quasars are often found in the early universe, at times when galaxies were still young and full of gas. Back then, conditions were more favorable for rapid black hole growth. Galaxies were colliding, gas was plentiful, and gravitational forces were stronger due to the closeness of matter. Hyperluminous quasars are like fossils from that time. snapshots of black holes during their most active and chaotic phase. The light from these quasars can also act like a flashlight, shining through the gas between galaxies. As it travels toward Earth, it passes through clouds of hydrogen and other elements which absorb certain wavelengths. By studying these absorption lines, astronomers can learn about the makeup of the early universe. In this way, hyperluminous quasars become tools not just for studying black holes, but for probing the cosmic web itself. A famous example of such a quasar is J 2157-3602, discovered only a few years ago. This object lies over 12 billion light-years away, and its brightness is staggering. Its central black hole is estimated to be over 30 billion solar masses, and it's thought to be accreting near or even above the Eddington limit. The amount of energy being released is hard to imagine. If it were placed in our own galaxy, its light would outshine every star in the sky combined, and it would likely blow apart the Milky Way's delicate structure in the process. When a black hole is feeding at these rates, it produces massive outflows of gas. These winds and jets can stretch thousands of light-years, slamming into the interstellar medium and stirring things up. In some regions, this might strip galaxies of the gas they need to form stars. In others, the shock waves might compress gas clouds, leading to bursts of star formation. The effects are complex and depend on the balance between heating and pressure. The feeding frenzy of hyperluminous quasars also seems to be short-lived. A black hole cannot sustain such a high rate of growth forever. Eventually, the fuel runs out, or the radiation pushes too hard and blows the surrounding gas away. When that happens, the quasar dims, the black hole quiets down, and the galaxy returns to a more peaceful state. What's left behind is a heavier black hole and a galaxy forever shaped by its central engine. Because they are so far away, their light is faint by the time it reaches us, and it often gets stretched and distorted by the expanding universe. It takes sensitive telescopes and careful measurements to identify them and estimate their properties. But thanks to modern observatories like the Very Large Telescope in Chile, the Sloan Digital Sky Survey, and JWST, astronomers are discovering more of these cosmic giants every year. The data from these observations not only reveal the brightness and distance of these quasars, but also tell us about the speeds of the material around them. By measuring how wide certain spectral lines are, scientists can estimate how fast the gas is moving. And from that, they can infer how massive the black hole must be to keep that gas in orbit. The wider the line, the faster the gas, and the heavier the black hole. As new discoveries continue, the picture of how black holes grow is getting more complex, but also more exciting. Hyperluminous quasars show that under the right conditions, black holes can go through wild phases, brief moments of furious energy where the rules bend and new structures are born. Giant molecular clouds, the underappreciated behemoths of star birth. Giant molecular clouds are vast, cold, and dark structures made mostly of hydrogen gas. Though they do not shine, they are where stars are born. Without them, galaxies would be nothing more than quiet collections of dead stars and fading light. These clouds are often overlooked in stories about the universe, yet they are the starting point for nearly all the light we eventually see. A giant molecular cloud, or GMC, is not a solid object. It's more like a thick fog made of gas and dust, drifting through the galaxy. Some are small, maybe just a few light-years across, but the largest can stretch over hundreds of light-years. The mass of one of these clouds can be huge, sometimes 1,000,000 times more than our Sun. Still, they are so spread out that to the eye, they can seem empty. Their true presence becomes clear only when studied through radio waves and infrared light, which can cut through the dust and reveal the dense knots hidden inside. These clouds are made mostly of molecular hydrogen. That's two hydrogen atoms stuck together, forming a molecule. But because hydrogen doesn't easily emit visible light at the low temperatures found in these clouds, astronomers often track carbon monoxide instead. Carbon monoxide is far less common, but it gives off radio signals that are easier to detect, and where there is carbon monoxide, there is hydrogen. The temperature inside these clouds is incredibly low, often just 10 to 20 degrees above absolute zero. That cold allows molecules to form and stay together. It also slows down motion, which helps gravity take hold. Over time, certain parts of the cloud can get denser. As the gas piles up in these pockets, gravity begins to win. The cloud collapses in on itself, and star formation begins. These birthplaces of stars are often hidden. We don't see the stars form directly, at least not in visible light, because the dust inside the cloud blocks it. But with infrared telescopes, we can peer into these dusty regions and see the glow of young stars. Some are still wrapped in gas, not yet fully formed. Others have already begun to shine, heating the cloud around them and pushing away the dust that once hid them. A single GMC can give rise to hundreds or even thousands of stars over time. Some will be small and dim, others large and bright. Sometimes the stars form in clusters, packed close together. Other times they are more spread out. What makes this even more interesting is how the birth of one star can trigger the birth of others. When a large star forms, its light and winds can push on the gas nearby, squeezing it and starting the next round of star formation. One of the most well-known examples of a star-forming region is the Orion Molecular Cloud Complex. This cloud, located about 1,300 light-years from Earth, includes the famous Orion Nebula. The Orion Nebula is only a small part of a much larger structure that spans hundreds of light-years. This entire complex is one of the closest examples we have of a giant molecular cloud at work. Further away, clouds like the Carina Nebula or the Eagle Nebula show even more dramatic results. These regions contain clusters of massive young stars surrounded by thick pillars of gas and dust. In images taken by space telescopes, these pillars look like sculptures, shaped by the winds and light of newborn stars. They show the raw power of the process, how the calm of the cloud gives way to the violence of starbirth. Not all parts of a GMC will form stars. In fact, much of the gas may remain quiet for millions of years. It takes the right conditions, enough density, low enough temperatures, and sometimes an outside push to get things started. Sometimes that push comes from a nearby supernova. Other times, the movement of the galaxy itself. Its spiral arms, its gravity, or even a collision with another cloud can do the trick. As stars form, they begin to change their surroundings. The most massive stars live fast and die young. Their strong radiation carves out bubbles in the gas. Their winds push the cloud apart. When they explode, they send even more energy into the cloud, breaking it apart and ending the star-forming process in that region. The cloud, once a nursery, is now a graveyard. What remains is gas blown into space, some of which may one day become part of a new cloud, starting the cycle over again. Despite their importance, GMCs are hard to study in detail. They are big, but also dim. They stretch over wide areas of the sky, so it takes time to map them out fully. Still, with modern tools like radio telescopes and space observatories, astronomers have made progress. Surveys of our own Milky Way have revealed hundreds of GMCs. Some are known only by their catalogue numbers, others by the star-forming regions they contain. Outside our galaxy, we see similar structures in nearby galaxies, like the Large Magellanic Cloud or Andromeda. In starburst galaxies, where stars are forming rapidly, GMCs are more active and more tightly packed. These galaxies often look bright and full of color, glowing with the light of countless young stars. That light traces back to the silent, dark clouds that started it all. The rate at which a galaxy forms stars depends on how many clouds it has and how active they are. Some galaxies form stars quickly, burning through their gas in a short time. Others move more slowly, forming stars over billions of years. The difference often comes down to the behavior of these clouds, how they form, how they collapse, and what forces act on them. It's easy to overlook something that doesn't shine, but giant molecular clouds are among the largest structures in a galaxy. They are quiet, cold, and dark, but inside them, stars come to life. They are the raw material of stars, planets, and everything that follows. Though they fade into the background, they hold the beginnings of almost everything we see in the night sky. Defining galaxy size, effective radius, luminosity profile, and dark halo extent. Galaxies themselves come in many shapes and sizes. Some are small and faint, with only a few million stars. Others are giant and bright, stretching across hundreds of thousands of light years. But when scientists talk about the size of a galaxy, it's not always as simple as measuring from edge to edge. That's because galaxies don't have solid borders. They fade out gradually, and their outer regions can be difficult to see. So instead of one fixed measurement, astronomers use several different ways to describe a galaxy's size. These methods depend on what part of the galaxy they're looking at, whether it's the stars, the light, or the invisible dark matter that surrounds it all. One of the most common ways to describe a galaxy's size is called the effective radius. This is the distance from the center of the galaxy, where half of its total light is contained. If you could see the galaxy as a glowing disk and draw a circle around it that holds 50% of the light, that circle's radius is the effective radius. It gives astronomers a useful average size that's easy to compare between different galaxies. Bright central regions weigh heavily in this measure, so it tends to focus on the galaxy's inner parts, where most of the stars are packed. But not all galaxies shine the same way. Some have bright, dense cores that quickly drop off in brightness, while others have more even light spread across their disks. To understand this better, astronomers use something called a luminosity profile. This is a graph that shows how the brightness of a galaxy changes with distance from its center. In spiral galaxies, the profile usually falls off smoothly, following what's called an exponential curve. In elliptical galaxies, which are rounder and more uniform, the profile often follows a different pattern, called a de Vaucouleurs profile, which falls off more slowly at large distances. These light curves help astronomers understand how stars are distributed across the galaxy and how its structure has changed over time. Some galaxies also have faint outer halos made of old stars. These halos can stretch much farther than the bright central regions, but they're hard to detect. They blend into the background and require sensitive instruments to study. Sometimes, when telescopes are powerful enough to detect this faint light, the galaxy turns out to be much larger than originally thought. This shows that the visible parts of galaxies are only one layer of their total structure. Beyond the stars and the light is dark matter. This invisible substance makes up most of a galaxy's mass, but doesn't glow, reflect, or absorb light. We know it's there because of the way it affects gravity. The stars in galaxies orbit much faster than they would if only visible matter were present. That extra gravity comes from a huge halo of dark matter that surrounds the galaxy. These dark halos can stretch far beyond the edges of the visible galaxy, sometimes up to 1 million light-years or more. They don't have sharp edges, but rather fade gradually, just like the stars do. Defining their size is even harder than defining the size of the visible part. Still, astronomers try to describe them using something called the virial radius. This is the region around the galaxy where the dark matter is dense enough to be considered part of the system. Beyond that, the dark matter blends into the general background of the universe. To figure out the size of a galaxy's dark matter halo, scientists use many tools. One method is to study the way stars and gas move within the galaxy. The faster the movement, the stronger the gravity, and the more mass must be present. Another method is gravitational lensing. This happens when a galaxy or cluster of galaxies bends the light from objects behind it. By measuring how much the light is distorted, astronomers can estimate the total mass of the foreground galaxy, including its dark matter halo. These measurements show that dark matter halos are usually about 10 to 100 times more massive than the stars and gas in the galaxy. They also spread out over much larger areas. For example, the Milky Way has a visible disk that's about 100,000 light-years wide, but its dark matter halo might reach more than 1 million light-years across. That means most of the Milky Way's size and mass is invisible to the eye. In some cases, the size of the dark halo helps explain other features of the galaxy. For instance, larger halos tend to have more gas and are more likely to form stars. But if the halo is too small or too hot, it might prevent gas from cooling and forming stars at all. This may be why some galaxies look like big dark matter clouds with only a few scattered stars. Others may have had more stars in the past, but lost them due to collisions or internal changes. Galaxy mergers can also change how size is measured. When two galaxies collide, their stars and dark matter mix, and their halos can overlap and stretch into new shapes. This can make the final system much larger than either galaxy was before. These events often leave behind long streams of stars and gas, called tidal tails, that extend far from the main body of the galaxy. There's another important point when thinking about galaxy size. Just because a galaxy looks big doesn't mean it's more massive. Some galaxies, like giant ellipticals, are very dense and hold lots of stars in a compact space. Others, like low-surface brightness galaxies, spread their stars over a wide area and appear faint, even though they are large. This means that size and mass aren't always directly connected. You need both light measurements and gravity estimates to get the full picture. In the nearby universe, we can study galaxy sizes in detail using high-resolution telescopes. We can trace their light profiles, measure their rotation curves, and map their outer halos. But in the early universe, it's harder. Distant galaxies appear much smaller and fainter, and their light is stretched by cosmic expansion. Even so, astronomers have found some ancient galaxies that seem unusually compact, much smaller than galaxies of similar mass today. This suggests that galaxies grow over time, building up outer layers through mergers and the gradual pull of gas and stars. New surveys using radio, infrared, and X-ray telescopes are pushing the boundaries of what we can detect. By combining observations across many wavelengths and using advanced models, astronomers are building a clearer map of the galaxy landscape. They are learning how galaxies form, how they grow, and how their sizes reflect the deeper forces of the cosmos. IC 1101, magnitude and dimensions of the largest elliptical galaxy. Located at the heart of the Abell 2029 galaxy cluster, IC 1101 is a giant elliptical galaxy, meaning it doesn't have spiral arms or a well-defined disk like our Milky Way. Instead, it appears as a smooth, rounded light profile that fades outward in all directions like a glowing sphere. IC 1101 sits about 1 billion light-years away from Earth. At this distance, it isn't something you can see with the naked eye, and even telescopes don't easily reveal its full outline. Much of its outer halo blends into the cluster environment, making its borders difficult to pin down. Still, measurements based on how its light spreads suggest it may stretch over 500,000 light-years across. That makes it more than 5 times wider than the Milky Way. The galaxy likely formed through many mergers. As part of a dense cluster like Abell 2029, it sits in an area where galaxies collide and merge often. Over billions of years, smaller galaxies fall into the center of the cluster, where they are torn apart by gravity. Their stars are absorbed into the central galaxy, slowly building up its size and mass. This galactic cannibalism is thought to be the main reason IC 1101 is so large. It grew through many slow interactions, collecting stars from nearby galaxies again and again. When scientists study IC 1101, they find a high number of old stars. These stars are reddish in color and burn through their fuel more slowly than younger, hotter blue stars. The lack of young stars suggests that this galaxy stopped forming new stars long ago. Much of the cold gas needed for star formation has likely been heated or blown away, either by earlier bursts of star formation or by the action of its central supermassive black hole. That means IC 1101 is not just a large galaxy, it's also a quiet one in terms of activity. It no longer produces many stars, and instead shines mainly from the light of billions of aging suns. At its center, like many large galaxies, IC 1101 hosts a supermassive black hole. The black hole in IC 1101 is believed to be among the heaviest in the universe, although the exact number is hard to pin down. Based on its mass and the brightness of the surrounding galaxy, some estimates suggest it could exceed 40 billion solar masses, placing it in the same class as other record-setting black holes, like the one inside TON 618. The galaxy's position at the center of Abell 2029 adds another layer to the story. This galaxy cluster is filled with hundreds of other galaxies, all bound together by gravity. IC 1101 isn't just one of the galaxies in this group. It's the brightest cluster galaxy, or BCG. These types of galaxies are almost always the largest members of their clusters. They sit in the deepest part of the cluster's gravity well, where material tends to gather over time. Because of this central location, IC 1101 has more opportunities to interact with other galaxies, drawing them in as they pass close by and absorbing them over time. This environment is also rich in dark matter. The cluster as a whole is held together by a massive dark matter halo, which affects the way galaxies move within it. IC 1101 lies at the center of this dark matter concentration. Its position there helps it remain stable and dominant, even as galaxies move and collide around it. This is part of what allows it to keep growing without being broken apart by gravitational forces. The space around IC 1101 is filled with hot gas. X-ray telescopes can detect this gas, which reaches millions of degrees in temperature. This gas is a sign of the cluster's mass, and also a clue about the processes shaping IC 1101. When galaxies fall into the cluster, the hot gas can strip away their cooler material, making it harder for them to form stars. Some of that stripped material can later be pulled into the central galaxy, adding to its size and giving it more mass over time. It is much more luminous than most galaxies, and the light extends outward in a diffuse halo, a feature often seen in central ellipticals that have grown by absorbing many smaller companions. These halos can stretch so far that they blend into the light from other cluster galaxies, making it difficult to tell where one galaxy ends and another begins. While many galaxies are part of clusters, only a few sit at the center and grow to such enormous sizes. Studying IC 1101 helps astronomers understand the limits of galactic growth and the forces that drive it. It shows how the environment plays a major role. It's not just about how much gas or dark matter a galaxy starts with. It's also about what happens as it interacts with its surroundings. Invisible giants, low surface, brightness galaxies like Marlin 1. In the vast spaces between the bright and familiar galaxies, there are others that almost seem like ghosts. These are low-surface brightness galaxies, systems that, despite sometimes being very large, remain nearly invisible in traditional sky surveys. They don't shine with the same strength as galaxies like IC 1101 or the Milky Way. Instead, their light is spread so thin that it barely rises above the glow of the background sky. One of the most famous examples of this kind is Marlin 1. Marlin 1 was discovered in the 1980s and surprised astronomers from the start. Not because it was bright or full of unusual features, but because it was so difficult to see at all. It was found using photographic plates, but not the ones meant for ordinary light. Instead, it appeared when astronomers used special filters and deep imaging, catching just the faint outline of something enormous. Once they realized what they were looking at, the true scale of Marlin 1 began to emerge. Marlin 1 is a spiral galaxy, but not like the ones most people imagine. Its core has some of the usual structure: a bright center, a rotating disk, some central concentration of stars. But then it fades outward into a disk that stretches well beyond what is seen in most spirals. Some estimates put its diameter at over 600,000 light-years, which would make it more than 6 times larger than the Milky Way. The outer disk is incredibly faint, which is why it remained hidden for so long. In fact, without specialized observing methods, it blends into the background noise of space. What makes low-surface brightness galaxies like Marlin 1 interesting isn't just their size, but how different their structure is from the galaxies we tend to see. Most of the galaxies found in early surveys were bright, compact, and easy to detect. Their stars were packed closely enough that the light stood out clearly on photographic plates. But low-surface brightness galaxies spread their stars out across a much wider area. Even though they might have billions of stars, those stars are so spread apart that the light from each region is dim. How do these galaxies form in such a way that they don't concentrate their stars more tightly? One answer may lie in how they handle gas. In typical galaxies, gas collapses under gravity to form stars, often creating bright clusters or arms. But in low-surface brightness galaxies, the gas is more diffuse. It doesn't collapse as easily. That means fewer new stars are born, and the ones that do form may be older and dimmer. Without the bright young hot stars that make other galaxies shine, these systems remain muted and quiet. There's also the issue of rotation. Galaxies spin because of the forces that shaped them early in the universe, and that spin helps determine how matter moves within them. In low-surface brightness galaxies, rotation curves suggest that a lot of the mass isn't in stars or gas, but in dark matter. Observations of Marlin 1 show that it rotates fast enough to suggest a large amount of dark matter is holding it together. Without it, the galaxy's thin outer regions might not have enough mass to remain stable. Surveys in the past relied heavily on brightness. When telescopes scanned the sky, they looked for areas with a sharp rise in light, spots that stood out against the sky's glow. This naturally led to a bias toward galaxies with higher surface brightness. That meant astronomers may have missed a whole population of faint giants lurking in the background. It's only in the last few decades, with more sensitive detectors and deeper surveys, that more of these hidden systems have come into view. Marlin 1 wasn't alone for long. As techniques improved, other similar galaxies were found. Some of them are even larger, and many of them show the same faint features: wide disks, few signs of new star formation, and rotation speeds that suggest lots of dark matter. Together, they form a class of galaxies that may be far more common than we realized. In visible light, they seem almost empty. But if you switch to other parts of the spectrum, like radio waves, you can detect more of their gas. Radio telescopes have found that many low-surface brightness galaxies have huge amounts of neutral hydrogen gas. That gas hasn't yet turned into stars, but it's there, waiting. This raises another mystery. Why hasn't the gas collapsed like it does in other galaxies? Some researchers think the environment plays a role. Galaxies that form in less crowded areas may avoid the collisions and interactions that trigger star formation. Without the pressure from other galaxies, their gas stays quiet and stable. Others suggest that feedback from early star formation or even weak activity from a central black hole might heat the gas just enough to stop it from collapsing. In either case, these galaxies remain stuck in a kind of slow-motion development, never lighting up the way brighter galaxies do. Low-surface brightness galaxies show that mass doesn't always mean brightness. A galaxy can be huge without being obvious. They also suggest that the range of galaxy types is broader than once believed. Rather than all galaxies following the same paths, there are many that take quieter roads, growing in the background while staying faint. Marlin 1 continues to be one of the best studied examples, though even now it isn't fully understood. Some of its features are hard to explain using current models. Its disk is so large and diffuse that it's unclear how it stayed stable during its formation. If it really is as big as measurements suggest, then it may point to an unusual history, perhaps shaped by early cosmic conditions that allowed it to form slowly over billions of years without much disturbance. Finding more galaxies like Marlin 1 is still a challenge. They require long observation times and careful analysis. But with modern sky surveys like those done by the Vera C. Rubin Observatory and other deep-field missions, astronomers expect to uncover many more. ESO 383, 76, the largest galaxy. ESO 383, 76, the reigning heavyweight of the cosmic arena, is a supergiant elliptical so enormous that it makes our Milky Way look like a humble speck in comparison. Nestled roughly 654 million light-years away in the constellation Centaurus, this celestial behemoth dominates its neighborhood, commands the hot gas of its cluster, and tells a story of cosmic growth on a truly epic scale. In the late 1980s, wide-field photographic studies revealed that at the level where 90% of its light has been counted, ESO 383, 76 stretches across a staggering 555.9 arcseconds. Translate that to real space at over 200 million parsecs away, and you get a diameter of roughly 1.8 million light-years, nearly 20 times the width of our own galaxy. The galaxy sits at the very heart of Abell 3571, a rich cluster of hundreds of companion galaxies. As the BCG, it sits like a king on its throne, shaping the motions of surrounding galaxies and corralling swaths of hot gas that glow fiercely in X-rays. In fact, ESO 383, 76 ranks among the top X-ray sources in the entire sky, so bright that space telescopes can pick it out with ease. That blazing halo of superheated gas marks out the gravitational well that ESO 383, 76 commands, pulling in matter from far beyond its stellar boundaries. Walk up to its outskirts, and you won't find neat spiral arms or bright blue star clusters. Instead, you encounter a soft, diffuse halo of ancient stars, their reddish light a testament to billions of years of quiet aging. ESO 383, 76 is a cosmic senior, with most of its star creation long past. Its E5 shape, stretched into an elongated ellipse, hints at a turbulent youth. Collisions and mergers with smaller galaxies have left their mark, warping its form and adding to its vast halo. You can almost read its history in the shape of its light. Zoom into the core, and you confront another heavyweight contender, a supermassive black hole, estimated at anywhere from 2 to 28 billion solar masses. Powerful jets and winds blast into the surrounding gas, regulating any residual star formation and heating the intra-cluster medium. ESO 383, 76's story stretches back billions of years to when the early universe's giant clouds of gas first collapsed under their own weight. Over time, smaller galaxies wandered too close and were swallowed whole. Their stars assimilated into ESO 383, 76's halo. Streams of stellar debris, detected in deep imaging surveys, trace these ancient mergers, fossil records written in faint light. Modern telescopes, like those behind the DESI legacy imaging surveys, have peeled back layers of darkness to reveal these ghostly ribbons of stars, offering clues to how this monster galaxy assembled itself piece by piece. Surrounding ESO 383, 76 is the vast Abell 3571 cluster, which itself may be part of the mighty Shapley supercluster. Here, hundreds of galaxies jostle and swirl, bound together by gravity and immersed in a sea of hot plasma. In this bustling environment, galaxies collide, gas is stripped away, and dark matter weaves an invisible web. ESO 383, 76 is surprisingly modest in visible light. At around magnitude 11.2, it requires a decent amateur telescope under dark skies to spot its faint extended glow. Point your eyepiece its way and you'll see a soft reddish smear, nothing like the bright pinpoints of stars you're used to. But look with X-ray eyes and the story changes. You find a powerhouse of hot gas and energetic phenomena, radiating with intense heat and revealing the true scale of its influence. Chandra and XMM Newton have mapped the X-ray glow, tracing how jets from the central black hole carve bubbles in the hot gas. Wide-field optical surveys have helped capture ever fainter tidal tails and streams, relics of past meals that ESO 383, 76 has digested. And the next generation of giant telescopes promise to peer even deeper, perhaps uncovering the earliest building blocks of this leviathan. Will they find relic star clusters that predate the galaxy's main growth phase? Or filaments of dark matter guiding new galaxies into its grip? In a universe filled with galaxies of all shapes and sizes, ESO 383, 76 stands out as a true outlier. It challenges our ideas of how big galaxies can get and how they interact with their surroundings. When you consider the Milky Way, with its 100,000 light-year span and calm spiral arms, you realize how extreme ESO 383.76 really is. It's a reminder that nature can produce structures of almost unimaginable scale, where hundreds of billions of stars roam across distances so vast that our human minds struggle to grasp them. Lyman alpha blobs, ethereal colossi from the universe's youth. In the early universe, long before galaxies took the familiar shapes we see today, strange glowing clouds marked the sky. These were not stars or galaxies. They were giant ghostly structures of gas, billions of light years away, known as Lyman alpha blobs. These blobs shine with a soft but powerful light, in a unique color given off by hydrogen gas. This light, called Lyman alpha radiation, comes from a process that takes place when hydrogen atoms are excited and then lose energy. The result is a signature wavelength that astronomers use to trace hydrogen in the cosmos. Lyman alpha blobs are some of the largest known individual objects in the universe by volume. They can stretch hundreds of thousands of light-years across, larger than even some of the largest galaxies. Despite being made mostly of gas, they shine with a distinct glow that travels across billions of years of space and time to reach Earth. This makes them one of the few ways we can directly observe the raw material of the early universe on such a large scale. The first Lyman alpha blobs were discovered in the late 1990s and early 2000s, when astronomers were conducting deep sky surveys to find galaxies from the early universe. Instead of finding only galaxies, they came across faint, diffuse patches of light that didn't look like anything familiar. These blobs were large, slow-moving, and glowing with the Lyman alpha emission line. They were found at high redshifts, which means they are very far away, and we are seeing them as they looked more than 10 billion years ago. One of the most famous Lyman alpha blobs is Labi 1, located in the SSA 22 region of the sky. Labi 1 spans nearly 300,000 light-years across, 3 times the diameter of the Milky Way. What makes Lab 1 and others like it so mysterious is the unclear source of their glow. They are not lit by a single bright object like a quasar or a starburst galaxy. Instead, their light seems to come from the gas itself, as if it is glowing without a clear external power source. This has led to several possible explanations, each with its own challenges. One idea is that the light comes from intense star formation happening inside hidden galaxies within the blob. These newborn stars could be giving off strong ultraviolet radiation, which then excites the surrounding hydrogen gas and causes it to emit the Lyman alpha light. But in many cases, the galaxies inside the blobs are too faint or too small to explain the entire brightness of the blob. That suggests that something else might be happening. Another possibility is that the blobs are powered by active black holes. These black holes, like those found in quasars, can heat up gas and make it glow, but not all blobs show signs of having black holes at their centers. In fact, some appear to be quiet, without the telltale emissions of active galactic nuclei. That weakens the black hole theory for at least some of these objects. There is also a third idea, that the blobs are glowing because of the way gas falls into dark matter halos in the early universe. In this view, cold hydrogen gas is being pulled by gravity into large, invisible structures made of dark matter. As the gas falls, it gets compressed and heated, and the energy released shows up as Lyman alpha radiation. This would mean the blobs are tracing the birthplaces of massive galaxies or even clusters of galaxies. They would be like cosmic cocoons, wrapping around regions where future structures are forming. Lyman alpha blobs are hard to study. Their faint light can be absorbed or scattered by dust or other gas along the way, which makes it difficult to get a clear picture of what's going on inside. Even detecting the blobs in the first place requires deep, long-exposure observations using special filters that isolate the Lyman alpha wavelength. Once found, blobs often require follow-up observations with other tools, infrared, X-ray, and radio telescopes, to learn more about their contents and structure. Some blobs appear to contain multiple galaxies, often in the early stages of merging. These merging galaxies could help stir up the gas, creating shocks or turbulence that help light up the hydrogen. Others seem more isolated, with little evidence of stars or galaxies nearby. This diversity makes the blobs even more puzzling. It suggests that they might not all come from the same kind of process, and that Lyman alpha blob may be a broad label for several different phenomena. Despite their faintness, Lyman alpha blobs show us how gas collects, moves, and changes before it settles into stars and galaxies. They may represent an early stage of galaxy formation, before the stars and structures we recognize today begin to take shape. Or they might be leftovers from large-scale gas flows that fed the growth of galaxies and clusters. Telescopes like the Subaru telescope in Hawaii and the Very Large Telescope in Chile have been able to map these blobs in greater detail. They reveal that some blobs have complex shapes, with tendrils and streams of gas stretching in different directions. Some show signs of rotation, hinting that they might be forming disks or even early spiral structures. Others seem to be more chaotic, with no clear structure but with signs of inflow or outflow. There are also efforts to simulate Lyman alpha blobs using computer models of the early universe. These models try to reproduce how gas, gravity, and radiation work together to form large glowing clouds. Some simulations can match the size and brightness of the blobs, especially if they include cold gas falling into dark matter halos. But the details are still being worked out, and no single model explains all the observed features. Radio galaxy halos, invisible giants, painting the radio sky. In visible light, galaxies brighten the sky with their stars, gas, and dust. But beyond what the human eye or optical telescopes can see, there's another layer to the cosmos that glows in a different kind of light: radio waves. In this radio sky, galaxies can appear much larger than they do in visible light. Some of the most massive structures in this realm are radio galaxy halos. These are not formed from stars or bright gases, but from vast clouds of particles moving at nearly the speed of light, sending out radio signals across millions of light years. Radio galaxy halos are some of the largest structures associated with galaxies, often stretching far beyond the edge of the visible parts. In some cases, the radio emission reaches distances 10 times the size of the host galaxy itself. These halos are made of electrons spiraling around magnetic field lines at nearly light speed. As they spiral, they emit synchrotron radiation, a process that produces strong radio signals. Special radio telescopes are needed to map the faint glow that outlines these invisible giants. At the center of many radio halos is a galaxy with an active supermassive black hole. This black hole pulls in surrounding gas and creates powerful jets of energy. These jets blast outward in opposite directions, cutting through the interstellar and even intergalactic medium. As the jets travel, they carry particles and magnetic fields with them, forming large lobes that expand over time. These lobes are what radio telescopes detect as the halo of the radio galaxy. Some of the most famous examples include galaxies like Centaurus A, Cygnus A, and 3C 236. These galaxies show huge lobes extending well beyond their visible shapes. In the case of 3C 236, the radio structure is nearly 15 million light-years across. That makes it one of the largest known radio sources in the universe. The size and power of these lobes suggest that the central black hole has been active for a long time, pumping out energy for hundreds of millions of years. In optical light, many of the host galaxies look like typical ellipticals or bright central galaxies in clusters. There's no hint of the enormous structures surrounding them. Only when mapped in radio frequencies does the true scale become clear. The shape of a radio halo can tell astronomers a lot about what's happening in and around the host galaxy. Sometimes the lobes are straight and symmetric, showing that the black hole's jets are stable and shooting out in a steady direction. Other times the lobes are bent or twisted, which can happen when the galaxy is moving through a cluster, or if the jets hit areas of denser gas. These changes in shape act like footprints, recording the history of the galaxy's movement and activity. Over time, the particles in the radio lobes lose energy. They cool down and stop emitting strong radio signals. But in some cases, they can be re-energized by shocks, turbulence, or renewed jet activity. This creates complex radio structures with layers of emission from different ages. By studying these layers, astronomers can piece together a timeline of the galaxy's activity, much like rings in a tree trunk tell the story of its growth. In galaxy clusters, radio halos take on even larger forms. Instead of being tied to a single galaxy, these cluster-scale halos spread across the central region of the entire group. They can be millions of light-years wide and don't have a clear central source. These halos are thought to form from the motion and merging of galaxies inside the cluster, which stirs up the hot gas and magnetic fields. As the gas moves and collides, it energizes electrons that produce diffuse radio glow across the cluster. These halos are often seen alongside relics, large arc-shaped structures at the edges of clusters that may come from shock waves caused by past collisions. One of the challenges in studying radio halos is that they are very faint. They don't emit strong signals like the compact cores of quasars or pulsars. Their radio brightness is spread out over large areas, which means that sensitive wide-field radio telescopes are needed to detect them. Instruments like the Very Large Array, the Low Frequency Array, and the upcoming Square Kilometre Array are key tools in this area. These telescopes can map the sky at multiple radio frequencies, revealing the structure, age, and energy of radio halos. The frequency at which a radio halo is observed can also change what is seen. At lower frequencies, older and cooler electrons still emit, which helps trace the full extent of the halo. At higher frequencies, the emission comes mostly from fresher, more energetic particles. By comparing maps at different frequencies, astronomers can measure how the halo evolves over time and estimate when the activity that powered it began and ended. In some cases, the radio structures extend beyond what is expected from a single galaxy's energy output. This raises questions about whether other processes, like past galaxy collisions or massive inflows of gas, contributed to the formation of the halo. These interactions may not always be visible in other wavelengths, making radio observations a crucial way to detect what's happening behind the scenes. Because they are tied to the activity of supermassive black holes, radio halos also help link galactic and cosmic scale behavior. A black hole just a few dozen light-hours across can produce structures stretching across millions of light-years. That contrast in scale shows how small, dense objects can affect the largest systems in the universe. The jets and outflows from the black hole carry not only particles, but also momentum, energy, and magnetic fields, all of which shape the space around them. As new surveys continue and more halos are found, astronomers are starting to see patterns in their distribution. Certain types of galaxies in certain environments are more likely to produce radio halos. Some galaxies may go through multiple phases of radioactivity, each time creating a new set of lobes that build up over cosmic time. These patterns help researchers understand not only individual galaxies, but also how energy moves through the universe, from the center of a black hole to the outer reaches of a galaxy cluster. Superclusters, the bound giants of galaxy assemblies. Galaxies are rarely found in isolation. Even those that seem alone are usually part of something larger, tugged on by distant companions through invisible threads of gravity. As we pull back from single galaxies, then from groups and clusters, we eventually arrive at one of the largest forms of structure that still hold together under their own gravity: superclusters. These are enormous groupings of galaxy clusters, collections of collections, bound together not just by gravity, but by the shared history of how matter formed and moved in the early universe. Their size is staggering. Some stretch nearly 1 billion light-years across, containing tens of thousands of galaxies. That's quadrillions of stars, planets, and possibly civilizations, all swirling inside a structure that, by cosmic standards, is still held together. They're the closest thing the universe has to city-states, self-contained, but still part of a larger network. The Virgo supercluster is a familiar example. Our Milky Way galaxy is part of a smaller group, the local group, which includes Andromeda and about 50 other galaxies. The local group, in turn, sits within the Virgo supercluster, a much larger region that holds several galaxy clusters, including the prominent Virgo cluster at its heart. This whole structure spans roughly 110 million light-years. It's enormous by human standards, but modest compared to some of the true giants discovered farther out in space. The Laniakea supercluster is one of those giants. Named from the Hawaiian words meaning immense heaven, it was defined in 2014 based on the motion of galaxies through space. Instead of mapping where galaxies are and drawing lines around clusters, scientists used galaxy velocity data to find regions that move together toward a common center of gravity. This method showed that the Virgo supercluster is just a part of a much larger structure, Laniakea, which stretches over 500 million light-years and includes over 100,000 galaxies. At the core of Laniakea lies a region known as the Great Attractor, a dense area pulling galaxies towards itself with invisible strength. This discovery showed that what we thought of as boundaries were more like stepping stones in a grander cosmic arrangement. Other superclusters, like the Shapley supercluster, go even further in size and mass. The Shapley concentration lies about 650 million light-years away and is one of the most massive known structures in the local universe. It's packed with clusters and contains an enormous amount of mass, enough to affect the motion of the Milky Way and its neighbors. Scientists think its gravity might be part of what's steering our galaxy and others toward it, influencing the direction of our cosmic drift. What makes a supercluster is more than just the number of galaxies inside. It's about the way the galaxies and clusters behave. If they are gravitationally bound, that is, if they are moving in ways that suggest they're tied together and not just drifting apart, then they form a supercluster. This definition matters because not all big structures are bound. Some might just be temporary alignments, like clouds passing in the sky. Others, like Laniakea, show clear evidence of shared motion. Some superclusters are relatively compact, with their galaxies bunched tightly. Others are stretched out, like long cosmic rivers. Their shapes depend on the flow of matter in the early universe and how dark matter shaped their growth. Most of the mass in a supercluster is invisible, locked in dark matter halos around galaxies and spread across the space between them. Despite their size and power, superclusters are not eternal. Over time, the expansion of the universe works against gravity. In the very distant future, some of the looser connections between clusters may break as space itself stretches faster than gravity can pull matter back in. Only the most tightly bound cores, regions where gravity is strong enough, will stay together. The rest will drift apart as the universe becomes more and more isolated. Some researchers even debate whether certain structures called superclusters are really gravitationally bound. The word is sometimes used more as a description of large-scale clustering than as a strict physical definition. But for the clearest examples, like Shapley or Laniakea, the motions and concentrations of matter seem to confirm their status. They're coherent entities, pulled together by gravity and shaped by billions of years of motion through the expanding cosmos. Galaxies inside clusters often interact with one another, merging, colliding, or stripping gas through tidal forces. Inside a supercluster, these interactions happen on a broader scale. The environment is more crowded, which can influence how galaxies grow or fade. For instance, galaxies deep inside superclusters tend to have less gas, making them less active in star formation. This suggests that supercluster regions might act as giant star formation regulators, slowly shutting down the process through a combination of heat, pressure, and repeated encounters. Our galaxy is moving toward the Great Attractor, part of Laniakea, at hundreds of kilometers per second. But even the Great Attractor is being pulled towards something larger, the Shapley supercluster. This creates a kind of chain of motion, where each region is being tugged by the one beyond it, forming what some scientists describe as a cosmic tug-of-war. Understanding superclusters helps clarify how matter is distributed on the largest scales. It shows us not only where galaxies are, but where they're going, and it hints at the limits of gravity's reach in an expanding universe. Even in a universe 13.8 billion years old, things are still forming, still moving, still falling into place. Cosmic filaments, the intergalactic highways of matter. If you zoom out far beyond the scale of any single galaxy or cluster, a pattern begins to emerge. It's not random, and it's not uniform. Instead, it looks something like a web, long strands of material stretching across vast distances, forming a kind of cosmic network. These structures are called cosmic filaments. They are among the largest known formations in the universe, shaped by gravity, dark matter, and the slow movement of matter over billions of years. They link clusters of galaxies together and help build the large-scale structure of the cosmos. Cosmic filaments are made mostly of dark matter, gas, and galaxies. The dark matter forms the invisible framework, while galaxies and intergalactic gas trace its shape. When observed on large scales, hundreds of millions of light-years across, filaments look like threads, connecting bright nodes that are galaxy clusters. These connections span immense voids, areas of nearly empty space with very little matter. The result is a pattern called the cosmic web, where the visible universe is laced together like strands in a spiderweb. In the early days after the Big Bang, the universe was mostly a hot, smooth soup of particles. But small differences in density, tiny ripples in that early mix, gave gravity something to work with. Over time, these small clumps pulled in more matter. The regions of higher density grew into long, thin bridges of gas and dark matter, while the lower density areas became the voids. These bridges eventually shaped the paths along which galaxies formed and moved. Using computers to model the evolution of matter from the Big Bang to the present day, researchers can create digital versions of the universe. These simulations show how gravity pulls gas and dark matter into thread-like structures. One well-known example is the Millennium simulation, which tracks the distribution of matter in a box over 2 billion light-years across. It shows filaments forming naturally, connecting galaxy clusters and stretching across the simulated space, just like what is observed in the real universe. Galaxies in filaments are often stretched out along the direction of the filament. Their movements also tend to follow the same path, as if flowing down the length of the thread toward a larger cluster. This motion helps feed the growth of galaxy clusters, which act like gravity wells at the intersections of filaments. Another tool for studying filaments is the light from very distant objects, like quasars. As light from a quasar travels toward Earth, it passes through the gas between galaxies. Some of this gas lies in filaments, and it absorbs specific wavelengths of light, especially the Lyman alpha line. By looking at how quasar light is absorbed, astronomers can map out the gas and trace the presence of a filament, even when no galaxies are clearly visible. Filaments vary in size and shape. Some are narrow and straight, stretching between just two clusters. Others twist and turn, branching into multiple strands. Some are hundreds of millions of light-years long and contain thousands of galaxies. A few of the largest known structures in the universe are classified as filaments or related to filamentary networks. The gas inside filaments is mostly warm-hot intergalactic medium, or WIM. This gas is hotter than normal space, but not as hot as the plasma inside galaxy clusters. It can be hard to detect because it doesn't shine brightly in visible light. However, telescopes that observe in X-rays or ultraviolet wavelengths can sometimes detect this gas. Measuring the WIM in filaments helps solve a long-standing mystery in cosmology, where all the universe's missing baryonic matter went. According to models, about half of the normal matter in the universe was unaccounted for. Recent evidence suggests much of it may be hidden in the warm gas of filaments. Galaxies inside filaments tend to be more massive and often show signs of interactions or mergers. The environment along a filament can be dense enough to increase the rate at which galaxies form stars or collide with one another. This effect is less extreme than what happens in the cores of clusters, but still stronger than in isolated regions of space. Observations suggest that even the supermassive black holes at the centers of galaxies may align with the direction of their host filament. Cosmic filaments are also channels through which matter flows in the universe. They funnel gas toward growing galaxies, feeding star formation and helping shape the development of cosmic structures. Without them, the universe would be a much emptier place, with less structure and slower evolution. Some researchers have proposed that filaments might also act as conduits for dark matter, guiding its movement across the cosmos. If true, this would make filaments even more essential to our understanding of how the invisible components of the universe operate. Galaxy walls, stratified layers of cosmic architecture. While cosmic filaments act like bridges connecting clusters and galaxies in thin threads, galaxy walls go one step further. They form vast flattened sheets where multiple filaments line up, sometimes in parallel, sometimes interwoven, creating something that stretches not just in one direction, but across two dimensions. These structures are often hundreds of millions of light-years wide and tens of millions deep. The first signs of galaxy walls appeared in redshift surveys. These surveys map the locations of galaxies by measuring their light and determining how far away they are based on how much their wavelengths have been stretched by the expansion of the universe. When these surveys began to show that galaxies were not randomly distributed, but instead formed patterns, lines, clusters, and even planes, astronomers started to get a clearer sense of the cosmic web. The Sloan Digital Sky Survey, among others, played a key role in bringing these walls into focus. As data poured in, a new image of the universe began to emerge. Galaxies weren't just gathering in clusters or moving along filaments. They were also collecting in wide, dense sheets that seemed to define the boundaries of vast empty regions, called voids. These galaxy walls were the walls of the voids themselves. As if the universe was organized like foam, empty bubbles surrounded by ridges of matter. One of the earliest and most famous examples of a galaxy wall is the CFA2 Great Wall. Discovered in 1989, this structure spans more than 500 million light-years in length and contains thousands of galaxies. It was the largest known structure at the time, and it forced astronomers to rethink how matter was arranged on cosmic scales. The Great Wall was not just long, it was thick, with galaxies arranged in a dense slab that had real depth, not just a thin ribbon or line. Later surveys revealed more of these walls. The Sloan Great Wall, for example, extends over 1.3 billion light-years and was discovered in 2003. Like its predecessor, it is composed of many galaxy clusters and filaments that align along a massive planar structure. Unlike a filament, which is typically long and narrow, a wall like this has clear width and height. It is not just a single path, but more like a continent in space, filled with cities of galaxies. The Pisces-Cetus supercluster complex extends through several constellations and includes multiple superclusters. It acts as a kind of wall segment within the greater web of structure, helping shape the flow of galaxies and gas in its region of space. These walls are like dividing lines between enormous regions of space. On either side of a wall, there are often voids, huge, dark stretches that contain few galaxies at all. The contrast is striking. One side might be filled with luminous matter, packed into a wide sheet, while just beyond lies a deep emptiness where only a handful of galaxies drift in isolation. This pattern repeats across the universe, giving it a sponge-like texture on the largest scales. Simulations of the universe's growth over billions of years show how these walls can form. Regions with more matter pulled in even more, while emptier regions were left behind. This process eventually created the filamentary web, but where multiple filaments intersected and aligned, sheets of matter formed, galaxy walls. Simulations that include dark matter show how it flows along filaments and builds up at junctions, forming walls and clusters. Without dark matter, these walls would likely not exist, at least not in the same way. When astronomers run models of the universe from just after the Big Bang to the present day, The large-scale patterns that appear often include filament and wall structures that look very similar to what we observe. This agreement helps confirm that the basic framework of modern cosmology is on the right track. In certain cases, what looks like a single structure may actually be multiple overlapping walls, formed from different filaments coming together at different times. These layered structures give a kind of three-dimensional texture to the walls, making them even more intricate. Galaxies within walls are often found to have different properties than those in less dense areas. They may form stars more quickly, interact with neighbors more often, and experience stronger gravitational effects. This allows astronomers to examine how environment affects galaxies over billions of years. The Sloan Great Wall: Lessons and Unanswered Questions. When the Sloan Digital Sky Survey began scanning the night sky in the early 2000s, few expected that one of its earliest breakthroughs would reshape how astronomers thought about the large-scale structure of the universe. The project was designed to be comprehensive, using a telescope in New Mexico to measure the positions and redshifts of millions of galaxies. From these measurements, astronomers could build a three-dimensional map of the cosmos. In 2003, buried in that data, researchers found something enormous. A formation so large it seemed to stretch the boundaries of what a universe shaped by gravity alone should be able to build. They named it the Sloan Great Wall. Unlike earlier discoveries of cosmic walls and filaments that were based on smaller galaxy catalogs or patchy sky coverage, the Sloan Great Wall was revealed with unprecedented clarity. It spans more than 1.3 billion light-years in length and is located roughly a billion light-years away from Earth, in the direction of the constellations Leo, Coma Berenices, and Virgo. The Sloan structure was the first that truly made astronomers pause and question how the universe could support such massive, coherent patterns of matter. The Sloan Wall wasn't a random scattering of galaxies. It showed a clear alignment, a superstructure of galaxy clusters and filaments, all connected into a vast sheet-like structure. The CFA-2 Great Wall had been identified decades earlier, but the Sloan Wall dwarfed it. It wasn't just longer, it was better defined, better sampled, and harder to dismiss as a statistical quirk. Thanks to the Sloan survey's depth and wide sky coverage, astronomers could observe the full extent of the structure in a way that wasn't possible before. The wall was seen as a clear, contiguous overdensity of galaxies, spanning hundreds of millions of light-years across its width and depth. At the time, most theoretical models predicted that large-scale structure should start to average out on scales larger than 300–400 million light-years. This is where the universe was expected to become homogeneous. It was thought that gravity, acting over billions of years, could cluster matter into galaxies, groups, and clusters, but that these would not align themselves into vast structures extending over a billion light-years. The existence of the Sloan Wall stretched these assumptions. It didn't necessarily break the rules, but it tested their limits. The wall also sparked renewed interest in studying galaxy bias, the idea that galaxies don't perfectly trace the distribution of dark matter. Since dark matter makes up most of the universe's mass, it's supposed to guide the formation of cosmic structures. But galaxies, being made of normal matter, may not always appear in the exact places where dark matter is densest. The Sloan Wall posed an open question. Did this structure represent an extreme overdensity of matter, or was it just a surface illusion caused by how galaxies light up parts of the cosmic web? Answering that question would require better simulations and more refined ways of linking dark matter maps to galaxy maps. Another lesson from the Sloan Wall was about the role of survey design. The Sloan Digital Sky Survey, with its wide field and deep coverage, was uniquely suited to discovering such a structure. Earlier surveys had been narrower or shallower, only catching hints of the large-scale structure. The Sloan Wall became a case study in how the scale of observation can define what you see. If a survey only looks at a narrow slice of the sky, large structures might appear broken or incomplete, but a wide, deep survey could reveal how galaxies group together into long walls, threads, and voids. The Sloan Wall may have always been there, but it took a new kind of data to fully reveal it. There were also puzzles. For one, simulations that matched the standard cosmological model did not frequently produce structures as large as the Sloan Wall. This didn't mean the wall couldn't happen, but it suggested it was a rare feature. It raised a broader issue about statistical outliers in a universe governed by chance and gravity. If large walls like Sloan are uncommon in simulations, but appear more than once in real data, then either we've been lucky observers, or the models may be missing something. Another open question was whether the Sloan Wall was a truly gravitationally bound structure, or just a temporary arrangement of galaxies caught in a moment of cosmic evolution. On human timescales, everything in the universe seems static. But on cosmological timescales, galaxies move, clusters merge, and filaments shift. It's possible that what we see as the Sloan Wall today is not a single unified object, but a temporary alignment of matter. Galaxies and clusters all passing through a similar region of space at the same time, bound by large-scale gravitational flows, but not permanently stuck together. In the cosmic web, some filaments and walls are thought to be stable over billions of years, slowly feeding galaxies and clusters with matter. Others may be more fragile, appearing as overdensities for a while before dispersing or evolving into something else. Understanding the life cycle of something like the Sloan Wall could give insight into how the universe organizes itself and how long these massive formations last. The discovery of the Sloan Wall also helped spark interest in mapping voids, the opposite of galaxy walls. These voids are often underappreciated, but just as important. They help balance the scales of cosmic structure and influence how matter flows across the universe. In the region surrounding the Sloan Wall, astronomers began cataloguing vast voids that stretch for hundreds of millions of light-years, creating a foam-like appearance to the cosmic web. In the 2 decades since the Sloan Wall's discovery, more detailed surveys have expanded our map of the universe even further. The wall remains a benchmark, an early indicator that the universe was more structured and more complicated than once believed. While more recent discoveries have grabbed headlines with their even larger dimensions, the Sloan Wall remains special. It was one of the first structures that showed what modern astronomy could reveal when given the right tools and a wide enough view. It also forced theorists to take large-scale structure seriously. No longer was it enough to simulate galaxies or small groups. Entire walls of galaxies needed to be reproduced, understood, and explained. Cosmologists began improving their models, adjusting the initial conditions, and increasing simulation volumes to capture these kinds of structures. The Sloan Wall had set the bar. Giant quasar groups, supermassive black holes in massive assembly. While most quasars seem to be isolated, scattered evenly across the cosmic landscape, a few discoveries hint that some of them might be gathering together. These massive assemblies are known as giant or large quasar groups. These LQGs can span over 2 billion light-years, several gigaparsecs from one end to the other. These are real structures seen in deep space observations, mostly at high redshifts, which means they are being observed as they were billions of years ago, when the universe was less than a quarter of its current age. Quasars are rare, and they are typically observed at great distances. Their light has traveled for billions of years to reach us. In most deep sky surveys, astronomers might detect a few scattered across a patch of sky. But every once in a while, something unexpected appears. A patch of sky where there are not just 1 or 2 quasars, but dozens or more. In 2013, astronomers studying data from the Sloan Digital Sky Survey found one such patch. It was centered around a structure now known as the Huge LQG, or Huge Large Quasar Group. It included 73 known quasars and extended over 1.24 gigaparsecs in its longest dimension. According to the standard cosmological model, known as lambda cold dark matter, or lambda CDM, the universe should become statistically homogeneous on scales above about 250-300 megaparsecs. The Huge LQG is more than 4 times larger than that threshold, and it's not the only one. Other large quasar groups have been discovered in separate parts of the sky, though none quite match the sheer size of the Huge LQG. Are the quasars physically bound? Are they following the same gravitational flows, clustering together under the pull of dark matter and early cosmic inflation? Or is it possible that we are seeing a projection effect? This is part of the ongoing work that astronomers and cosmologists are still exploring. But the alignment and close proximity of these powerful sources suggests something unusual. These are not quiet, passive galaxies. They are sites of intense energy release, where black holes are actively growing by swallowing gas at extreme rates. Each quasar in one of these giant groups is thought to be located in the center of a young, rapidly growing galaxy. The central black holes are often billions of times more massive than the Sun and are accreting matter at speeds close to their theoretical maximum. That so many of them appear close together suggests that these regions are hotbeds of activity and where the conditions for black hole growth are especially favorable. It also implies something about the larger environment. Black holes don't grow in isolation. They need fuel, and they need a steady supply of matter. For dozens of quasars to ignite in the same region of space, there must be a dense environment of gas and dark matter. This aligns with the idea that LQGs trace the skeleton of the cosmic web. These quasar groups may be the signposts of where galaxy clusters and superclusters will eventually form, marking out the densest intersections of the cosmic web during the universe's youth. When astronomers look at the light from these quasars, they can measure redshifts and velocity distributions. Many of the quasars in these groups show similar redshifts, suggesting they are at nearly the same distance. And while their exact positions are spread out over hundreds of millions of light years, their clustering is statistically significant. Quasars are powerful emitters of ultraviolet and X-ray radiation. When multiple quasars are grouped together, their combined energy output could drastically reshape their cosmic neighborhood. They may heat up the intergalactic medium, change the chemistry of the gas, and suppress or trigger new rounds of star formation in nearby galaxies. If such structures are common, or if they occupy a significant fraction of the sky, then our assumptions about large-scale uniformity may need to be revised. It could mean that the early universe was more clumpy than expected, or that inflationary models need to account for stronger fluctuations in the density field. Hercules Corona Borealis, Great Wall, a contender for supremacy. In 2013, astronomers working with gamma-ray burst data plotted the distribution of these violent explosions across the night sky and noticed a strange pattern emerging. Gamma-ray bursts are thought to come from distant, high-energy events like the collapse of massive stars or the merging of neutron stars. They are rare and randomly scattered across the universe, so any noticeable clustering can point to something physically real. What the team found was a collection of gamma-ray bursts that appeared to be grouped over a vast area of the sky, an area far larger than anything previously observed. This discovery would come to be known as the Hercules Corona Borealis Great Wall. This enormous structure, if real, stretches over 10 billion light-years from end to end. That number is staggering. It places the Great Wall not only as potentially the largest structure ever identified, but also as one of the most puzzling. Its size challenges some of the basic expectations astronomers have held about how the universe is organized on the largest scales. The cosmological principle states that, on large enough scales, the universe should look the same in every direction. In other words, while things might be clumpy and uneven on smaller scales, like galaxies and clusters, eventually everything should average out. The cosmos, beyond a certain size, should be smooth, uniform, and isotropic. That assumption underpins the mathematics behind models of the Big Bang, cosmic inflation, and the expansion of the universe. Structures like galaxy clusters and walls were always expected to exist. The theory allows for things like the Sloan Great Wall or the CFA2 wall, as long as they stay within a few 100 million light-years. But the Hercules Corona Borealis Great Wall pushes those expectations to the edge, and maybe even beyond them. At over 10 billion light-years, it's too large, at least by current models. Some cosmologists have estimated that no structure larger than about 1.2 billion light-years should form under the influence of gravity since the beginning of time. If this wall is what it appears to be, then it may not be an outlier. It could be a sign that something is missing from the picture. The wall spans across several constellations, including Hercules and Corona Borealis, which gave it its name. What makes this wall even more strange is that it was found using gamma-ray bursts, not optical surveys. This means it's harder to confirm using the usual techniques. Gamma-ray bursts are brief and powerful. They don't come from a steady source like a galaxy, but from single catastrophic events. That makes them more difficult to track over time. But their brightness allows them to be seen from extreme distances, giving researchers a way to probe very early and far regions of the universe. The clustering of these bursts in one area, all at a similar redshift, which means similar distances and therefore a similar time period in the past, pointed to the possible presence of a massive underlying structure. The gamma-ray bursts, despite being random in origin, were not randomly placed in the sky. The researchers found a large group of them concentrated in a specific zone, which suggested they might all be coming from galaxies inside a vast structure. Still, because gamma-ray bursts are rare and spaced out in time, there's always the question of statistical noise. Could this clustering be a coincidence? Could the way the data was processed create a false signal? These are the questions that critics have asked. Not everyone agrees that the Hercules Corona Borealis Great Wall is a single coherent structure. Some suggest it might be multiple smaller structures that just happen to line up. Others wonder if it could be a fluke of observation. To be sure, more data is needed. But if confirmed, the wall forces a re-examination of what's possible in a universe shaped mostly by dark matter and dark energy. Current simulations based on these forces rarely show structures that reach even 1 billion light-years across. That's because the cosmic web grows slowly. It forms through the gentle pull of gravity acting over billions of years. It isn't expected to stitch together anything on the scale of this mega wall, not in the time available since the Big Bang. What might explain it? One idea is that cosmic inflation left behind imprints or seeds for large-scale structure. If inflation was more chaotic than expected, it might have created regions with unusual density fluctuations. These early seeds could have helped form bigger structures later on. Another possibility is that our understanding of dark energy, or the behavior of gravity on huge scales, needs refinement. If either of those forces behaves differently than current theories predict, it could allow for the growth of larger structures. The implications go beyond just one wall. If the universe can support the formation of a structure 10 billion light-years wide, then many assumptions about cosmic evolution may need to be revised. It could mean the universe is less homogeneous than we thought. It might also suggest that extreme structures are more common at certain epochs in cosmic history, or that early periods of galaxy formation were more efficient in certain regions. For many, the universe is already vast and difficult to grasp. But structures like this push the limits of human comprehension even further. They hint at an architecture to the universe that is both immense and intricate, built not just of galaxies and stars, but of entire collections of galaxy clusters shaped by forces we still don't fully understand. Voids of the cosmic web. Exploring enormous cosmic cavities. Cosmic voids are not just empty in the sense that they have no stars. They are the largest underdense regions in the universe, places where galaxies are rare, matter is thin, and activity is minimal. In many ways, they are the quiet side of the cosmos. Cosmic voids were first noticed as surveys began to map galaxy positions in 3 dimensions. In these early maps, clusters of galaxies were obvious, and between them were long, winding filaments. But what stood out just as much were the spaces in between, regions where galaxies were few and far between. These were not small gaps or pockets. Some were hundreds of millions of light-years across. One of the earliest and most famous examples is the Boötes void, discovered in 1981. It spans about 330 million light-years and contains only a few dozen galaxies, where thousands would be expected in a typical volume that size. Voids are surrounded on all sides by the denser components of the web, and their boundaries are often where filaments meet or turn. These voids are not perfectly spherical or completely empty, but they are far less crowded than their surroundings. The density inside a void can be as low as 10% of the average cosmic density, sometimes even less. If the filaments are the highways of galaxies, voids are the open deserts between them. Where galaxies cluster and grow in filaments, voids expand and cool. Gravity pulls matter away from the voids and toward the denser regions, making the voids grow over time. In fact, voids are one of the few large-scale features that become more distinct as the universe ages. As expansion continues, matter keeps draining from these under-dense regions, making them larger and emptier. Voids are the growing hollows of cosmic evolution, the negative imprint left by the clustering of galaxies elsewhere. Some galaxies do live inside voids, though they are usually different from their counterparts in denser regions. Void galaxies tend to be smaller, bluer, and more isolated. They have fewer neighbors and less interaction, which means their development is shaped more by internal processes than by mergers or external influences. Because they evolve differently from dense regions, they are sensitive to the properties of dark energy and the rate of cosmic expansion. As the universe expands, voids grow, and their shape and size can be used to test models of the universe. For example, certain theories predict slightly different expansion rates in different regions. By comparing the distribution and structure of voids in various directions and at different redshifts, astronomers can test these predictions. Another intriguing use of voids comes from a method known as the integrated Sachs-Wolf effect. This effect occurs when cosmic microwave background, or CMB photons, pass through large structures on their way to us. In dense regions, the photons gain and then lose energy as they pass through gravitational wells. But in expanding voids, the gravitational potential changes as the photon moves, leaving a slight imprint on the CMB. Measuring these subtle changes allows researchers to test the effects of dark energy over large scales. Since they are defined by what is not there, astronomers must work backward, first mapping where galaxies are, and then looking for the holes. Modern surveys like the Dark Energy Survey and future efforts are producing three-dimensional maps of galaxies at huge scales, which can then be used to identify and analyze voids more precisely. The boundaries of voids, the galaxies within them, and the relationships between voids and the rest of the cosmic web are being measured with increasing accuracy. Some voids are nearly spherical, while others are long and stretched. Some have filaments that stretch across them, linking the denser regions on either side. In other cases, mini-voids exist inside larger ones, like bubbles within bubbles. And not all voids are isolated. Sometimes several voids come together in a loose association, forming what some researchers have called supervoids. These massive cavities can span over 1 billion light-years, and their presence might even be linked to anomalies seen in the CMB, such as the famous cold spot, a region of the sky where the background radiation is slightly cooler than expected. There is still much to learn about what happens inside voids and how they influence the universe on a large scale. Can voids host dark matter in different ways? How do they grow? And could they help explain why the universe seems to be expanding faster than expected? These are ongoing questions. In the silence of the voids, the story of structure formation is written just as clearly as in the brightest galaxy cluster. It is a story of retreat rather than collapse, of dispersal rather than gathering. Yet it is no less important. Eridanus, supervoid, and the CMB cold spot, a mysterious connection. The CMB is spread almost evenly across the sky, but not perfectly. Tiny variations in temperature, just a few microkelvin, hold clues about how matter was distributed in the early universe. Most of these temperature changes make sense, matching the expected patterns of density and motion. But then there's the cold spot. The cold spot sits in the southern hemisphere of the sky. in the direction of the constellation Eridanus. It stretches over about 10 degrees of the sky, far larger than most other temperature anomalies in the CMB. The temperature difference is subtle, just a few hundred microkelvin colder than average, but that's enough to make it stand out. When the Wilkinson Microwave Anisotropy Probe and later the Planck satellite both confirmed its presence, it sparked a wave of curiosity. Was this just a rare statistical blip, or did it have a deeper cause? Around the same time that researchers were studying the cold spot in the CMB, other astronomers were mapping the large-scale structure of the universe in the same direction. What they found was unexpected: a vast, underdense region, now known as the Eridanus supervoid. It's one of the largest known voids in the local universe. The Eridanus supervoid is roughly 1 billion light-years across. For a long time, voids were thought to be smaller, usually a few hundred million light-years wide. But the Eridanus void seems to stretch farther and run deeper than most. Some estimates suggest that it is about 20% less dense than surrounding regions, a significant drop when viewed over such a large area. Its shape is a flattened, stretched-out depression in the fabric of the cosmic web. Perhaps the cold spot in the CMB isn't just a relic from the early universe. Maybe it's been affected by the structure of the modern universe through the integrated Sachs-Wolf effect. This effect leaves the photon with slightly less energy, making it appear cooler to us. In the case of the Eridanus supervoid, this could mean that photons traveling from the cold spot passed through the giant void on their way to Earth. As they crossed the underdense region, they would have been stretched and cooled more than average, creating the cold patch we see in the CMB. This explanation isn't universally accepted, but it is one of the leading theories connecting large-scale structure to early universe light. Simulations of voids in the universe suggest that the effect of even a very large void should not be strong enough to produce a cold spot as deep as the one we observe. The numbers don't always line up. The temperature difference caused by the integrated Sachs-Wolf effect in a void the size of Eridanus should be much smaller than what we see in the cold spot. This means that if the void is responsible, then it either needs to be larger and emptier than currently measured, or something else is contributing to the effect. Some scientists have proposed that the Eridanus supervoid could be a combination of multiple smaller voids lined up along our line of sight. This could make the total underdense path longer than a single void would allow, increasing the cooling effect on the CMB photons. But even this stacked void model struggles to fully explain the depth and shape of the cold spot. Others have looked for alternate explanations. One possibility is that the cold spot is a primordial feature, a leftover from the early inflationary period of the universe, when quantum fluctuations were stretched to cosmic scales. If this were true, then the cold spot might be a window into physics beyond our standard model, possibly even evidence of interactions with other universes or variations in the fabric of space-time itself. These ideas are speculative, and there's little direct evidence for them, but they show the lengths cosmologists are going to tackle this mystery. In a universe, this large, rare features are expected to show up just by chance. Some researchers argue that the cold spot might simply be a statistical fluke, a part of the normal variation in the CMB that just happens to look strange. They point out that once you start focusing on specific features after seeing them, the chance of them standing out increases. But others argue that its distinct appearance and the possible link with the Eridanus void make it worth deeper investigation. The connection between the Eridanus supervoid and the cold spot is one of those rare moments in science where two seemingly separate phenomena, early universe light and present-day cosmic structure, might be linked. If that link is confirmed, it would be one of the clearest examples of how large-scale structure affects the ancient light we still observe today. It would also add weight to our models of the expanding universe and the role of dark energy in shaping it. The particle horizon, the ultimate edge of the observable universe. Out in the farthest reaches of space, past all the galaxies and the glowing nebulae, beyond the great filaments, and even the vast voids that stretch across billions of light years, there lies a boundary. It's not made of matter. It's not a wall or a cluster or a barrier we can touch, but it is real, and in a very important way, it defines the edge of everything we can ever see. This boundary is called the particle horizon, and it marks the farthest limit of the observable universe. The particle horizon isn't a place you can visit, and it doesn't have any unique features. It's more like a line drawn by time and light, a frontier created by the rules of physics. It represents how far light has been able to travel since the beginning of the universe. And because light takes time to move, there's a natural limit to how far out we can look. That limit isn't set by technology or telescope strength. It's set by the speed of light and the age of the cosmos. The story of the particle horizon begins about 13.8 billion years ago, at the moment of the Big Bang. That's when space and time themselves began to expand. As soon as the universe was born, light started its journey. But that light could only travel so far, in any given amount of time. Just like how sound from a thunderclap takes time to reach your ears, light from distant parts of the universe takes time to reach our telescopes. And because the universe has only existed for a limited amount of time, there's only so much distance light could have traveled. This is why we see the universe as it was in the past. The farther out we look, the further back in time we're seeing. A galaxy that's 1 billion light years away is one we see as it was 1 billion years ago. A galaxy 10 billion light years away shows us light that started traveling when Earth didn't even exist yet. And the particle horizon marks the farthest distance that light could have traveled to reach us today, the outer edge of this vast cosmic shell of visibility. Now, at first, it might seem like this distance should just be 13.8 billion light years, because that's how old the universe is. But that's not quite right. The universe has been expanding the entire time light has been traveling. So, while the light we see today may have left a galaxy 13.8 billion years ago, that galaxy has moved farther away during that time due to the stretching of space itself. Because of this expansion, the current distance to the edge of the observable universe is actually much larger, around 46 billion light years in every direction. That gives us a total observable diameter of about 93 billion light years. This expanding horizon doesn't mean we're at the center of the universe. It just means we're at the center of our observable universe, our own personal bubble of what we can see. Every observer, no matter where they are in the universe, has their own particle horizon. It's like standing in a vast foggy field. No matter where you are, you can only see as far as the fog allows, but someone standing far away from you will see a different patch of land, defined by their own visibility. Everything inside this horizon is potentially observable, not just now, but in theory, at any point in time. That includes all the galaxies, stars, clusters, voids, and radiation we've studied. It includes the cosmic microwave background, which is the afterglow of the Big Bang and the oldest light we can detect. It includes structures like the Boötes Void, the Laniakea supercluster, and Hercules Corona Borealis Great Wall. But beyond the particle horizon, we can't know what's there. Light from those regions hasn't had time to reach us. It might be more of the same. More galaxies, more cosmic web, more structure. Or it might be different in ways we can't imagine. Whatever lies beyond is invisible, forever out of reach unless the universe changes in some dramatic way that alters the speed of light or the nature of space. This boundary isn't fixed in the way a wall is. It's more like a moving front, a shell of visibility that grows over time as light from more distant parts of the universe finally reaches us. With every passing year, the horizon stretches a little farther. But because the expansion of the universe is speeding up, there are regions of space that will never become visible. Some galaxies are already moving away from us faster than the speed of light due to this expansion. That means their light will never reach us, no matter how long we wait. The particle horizon is a reminder of how limited our view is, even with all our technology. The universe is likely far larger, possibly infinite, but we only have access to a slice of it, determined by time and light and the way space behaves. That slice is vast beyond imagination, but it's still a limit. No matter how much we observe, we're always looking out from one point through a window defined by the laws of physics. When mapping galaxies or studying background radiation, astronomers and cosmologists always keep the horizon in mind. It marks the outer edge of their data. When building models of the early universe, they use the horizon to figure out what signals should be detectable and which ones are beyond reach. And in theoretical physics, the horizon plays a role in discussions about inflation, the shape of the universe, and whether the cosmos wraps around in strange, unexpected ways. If we can't see beyond the particle horizon, how can we be sure what lies out there? Can we assume the universe is the same everywhere? Or might it be different in regions we'll never be able to observe? Is there something fundamentally unknowable beyond our cosmic horizon? These aren't questions that science can fully answer. There's a poetic quality to the particle horizon. Light has to work its way across space, and we're always watching it arrive after a long, slow journey. We are, in a very real sense, living inside a cosmic light bubble, surrounded by the past, shaped by what can reach us, limited by what hasn't arrived yet. It doesn't mark the end of the universe. It marks the end of what we can know, at least for now. Beyond it, space may continue forever. But from our small point within the vast cosmos, the particle horizon is where the universe fades into silence, where our gaze finally stops. Next-generation telescopes, probing scales never seen before. As we stand on the brink of a new era in astronomical observation, a series of next-generation telescopes are poised to revolutionize our understanding of the cosmos. These upcoming instruments, including the Vera Rubin Observatory, the Extremely Large Telescope and others, are set to overcome many of the challenges that have limited our ability to probe the vastness of space. These telescopes aim to observe the universe in unprecedented detail and at scales never before seen, tackling the very problems that have hindered our exploration of the largest and most distant objects in the universe. The Vera Rubin Observatory, currently under construction in the Atacama Desert of Chile, is one of the most anticipated observatories of the coming decade. It is designed to survey the entire sky in visible light, with a level of detail that has never been achieved before. One of the main goals of the Vera Rubin Observatory is to create the most comprehensive and detailed map of the night sky, known as the Legacy Survey of Space and Time, or LSST. With its wide-field camera and state-of-the-art imaging technology, the observatory will capture more than 800 images of the sky each night, scanning an area that is roughly 20,000 times larger than the full moon. This will enable the Vera Rubin Observatory to study not just individual stars or galaxies, but large-scale cosmic structures, including the vast filaments, walls, and voids that make up the cosmic web. By capturing such an enormous swath of the sky in such a short amount of time, the Vera Rubin Observatory will provide a more complete view of the universe than ever before. One of the significant advancements this observatory brings is the ability to observe dark energy and dark matter with far more precision than current instruments allow. By mapping the universe in greater detail, the LSST will allow astronomers to measure how galaxies are distributed and how they move, helping to illuminate the invisible forces that shape the universe. In addition to dark matter and dark energy, the Vera Rubin Observatory will offer new insights into the distribution of galaxy clusters, the motion of stars, and the behavior of large-scale cosmic structures. This observational power will be critical for studying massive objects, such as superclusters and large galactic walls, and will help to better understand the way the universe is organized at the largest scales. The sheer size of the observatory's field of view will enable it to detect rare and faint objects that would have been missed by previous surveys, adding a new level of depth to our knowledge of the cosmos. On a different scale, the Extremely Large Telescope, or ELT, being constructed by the European Southern Observatory at the Paranal Observatory in Chile, promises to push the limits of optical astronomy. When completed, the ELT will have a main mirror 39 meters in diameter, making it the largest optical telescope in the world. With this immense collecting area, the ELT will be able to gather light from distant and faint objects with unmatched precision. It will be capable of detecting objects billions of light years away with clarity and detail that current telescopes cannot achieve. One of the major breakthroughs enabled by the ELT will be its ability to directly observe and study exoplanets in ways that were previously impossible. Its enormous mirror and advanced adaptive optics system will allow it to reduce the blurring effects caused by Earth's atmosphere, enabling astronomers to directly image distant planets orbiting other stars. This will be especially important for studying the potential habitability of exoplanets and for understanding the diversity of planetary systems across the universe. But the ELT will not just focus on exoplanets. Its sheer size and sensitivity will enable it to probe the most massive and distant objects in the universe, including supermassive black holes, quasars, and galaxy clusters. The ELT will allow scientists to study the behavior of these objects with unprecedented detail, providing new insights into their structure, growth, and evolution. For example, by studying the accretion disks around black holes and the jets they produce, the ELT will help to uncover the fundamental physics that governs these mysterious objects. Like the Vera Rubin Observatory, the ELT will help to chart the cosmic web, but it will be able to do so with much higher resolution and in a much more detailed manner. Its powerful instruments will enable astronomers to study the distribution of galaxies and clusters, shedding light on the forces that shape the evolution of the universe. Another key development in the world of astronomical instrumentation has been the James Webb Space Telescope, or JWST, which, while not directly related to the upcoming optical telescopes like the ELT, represents a leap forward in infrared astronomy. Launched in December 2021, JWST is designed to study the universe in the infrared portion of the electromagnetic spectrum, allowing it to peer through cosmic dust clouds and observe objects that are too faint or distant for optical telescopes. One of the major advantages of infrared astronomy is its ability to observe extremely distant galaxies, stars, and even the first light from the Big Bang itself. The JWST's capabilities have already been instrumental in studying the earliest galaxies and the formation of the first structures in the universe. It will continue to help probe the formation of supermassive black holes and the growth of early galaxy clusters, providing new insights into how the largest objects in the universe took shape. By observing objects at very high redshifts, the JWST will offer a glimpse into the universe's infancy, allowing astronomers to trace the evolution of galaxies and cosmic structures from their earlier stages. Its infrared observations will also be used to study the composition and behavior of objects much closer to home, including the study of exoplanet atmospheres and the search for signs of habitability. As such, it complements ground-based observatories, providing a more complete picture of the universe from both a local and cosmological perspective. While the ELT and other large ground-based telescopes will be able to observe distant objects with incredible detail, they will still be limited by atmospheric interference. Even with adaptive optics technology, the atmosphere remains a significant obstacle to achieving perfect clarity, especially for objects in the most distant reaches of the universe. The Vera Rubin Observatory, while promising in terms of wide field surveys, will still face challenges related to data analysis. With the massive amounts of data generated by such a large survey, processing and interpreting the information will require new algorithms and techniques in data science. Additionally, the sheer volume of information will require an unprecedented amount of computational power to analyze, and the need for new technologies to handle and store this data will be a growing concern. Despite these challenges, the future of astronomical observation looks brighter than ever. As these next-generation telescopes come online and begin their observations, they will undoubtedly push the boundaries of what we understand about the universe. With every new discovery, we'll come closer to answering the profound questions that have long captivated humanity. What is the universe made of? How did it come to be? And where are we heading in the vast expanse of space and time? Beyond the observable, theoretical expanse of vacuum energy. As we peer out into the sky, our view of the universe is constrained by the finite speed of light and the finite age of the universe itself. But what lies beyond this boundary? This question, while inherently speculative, invites us to explore the realm of theoretical physics and cosmology. What might exist beyond the observable universe, in regions we cannot yet access or perhaps never will? Vacuum energy is the energy present in empty space, a form of energy that exists even in the absence of particles. Despite the name, empty space is far from truly empty. Quantum fluctuations in the vacuum give rise to transient particles and energy, and these fluctuations are thought to have influenced the universe's early expansion. The speculative nature of what lies beyond the observable universe is closely tied to the theories of inflationary cosmology and the behavior of vacuum energy on cosmic scales. According to the theory of cosmic inflation, the universe underwent an incredibly rapid expansion in its earliest moments, which set the stage for the universe's current structure and the distribution of matter and energy. However, the nature of inflation suggests that different regions of the universe may have stopped inflating at different times, leading to a patchwork of regions where inflation has slowed down, and those where it is still ongoing. The regions where inflation has slowed down, allowing the formation of galaxies, stars, and other structures, make up the observable universe. However, beyond this boundary, inflation could still be continuing in other regions, creating vast expanses of unobservable space that have never slowed down to form the structures we see in our part of the cosmos. One intriguing possibility is that beyond the observable universe, there could be regions of space where vacuum energy behaves differently. These regions could be home to entirely different cosmic laws or behaviors that we cannot yet detect or even imagine. In some models, these regions might contain enormous voids. On the other hand, there might also be regions of space where overdensities occur, where vacuum energy causes a faster than normal formation of matter. These areas could be the birthplaces of entirely new forms of matter that differ from anything we can observe within our own volume of space. It's even possible that these regions could lead to entirely different versions of the universe, operating under a set of physical laws or constants that differ from what we understand. In the context of vacuum energy, one of the most speculative theories is the notion of a multiverse, a collection of multiple universes, each with its own set of physical laws and characteristics. These universes could exist in separate regions beyond the observable universe, each undergoing its own process of inflation and expansion. According to some interpretations of the theory, our universe could be just one of many bubbles within a much larger foam of universes, with each bubble having different properties. This theory implies that beyond our observable universe, there could be an uncountable number of other universes with entirely different laws of physics. The concept of the multiverse challenges the idea that our universe is unique and suggests that there may be an infinite number of universes, each with its own version of space-time and fundamental constants. While the idea of multiple universes remains purely speculative, it has gained traction in some circles of theoretical cosmology, particularly in the study of string theory and the idea of eternal inflation. As the universe continues to expand, it is believed that the amount of vacuum energy in the universe will increase. This could lead to an accelerated expansion, pushing galaxies even further apart and creating a universe that becomes increasingly empty and cold. In some theories, this heat death scenario represents the ultimate fate of the universe, where all stars burn out and matter is spread thinly across an ever-expanding cosmos. Other theories, however, suggest that vacuum energy could eventually lead to a big rip, where the expansion of the universe accelerates so rapidly that galaxies, stars, planets, and even atoms are torn apart. These ideas are deeply tied to our understanding of fundamental physics and the fabric of space-time itself. By studying how vacuum energy behaves on large scales, cosmologists hope to unlock deeper insights into the forces that govern the universe's behavior and its ultimate fate. We are accustomed to asking questions based on empirical evidence, what we can observe, measure, and experiment with. But theories about vacuum energy, the multiverse, and cosmic inflation are speculative because they deal with realms that we can never directly observe. However, they are rooted in the mathematics of quantum mechanics, general relativity, and cosmology, and are deeply connected to the laws of physics as we understand them. At present, the only way to explore these distant, unobservable regions is through indirect methods. By observing the behavior of the cosmos within the limits of our observable universe, scientists attempt to infer what might be happening beyond. This can include studying the CMB for clues about the early universe, or using large-scale structure surveys to understand how galaxies and clusters are distributed. In this sense, our understanding of what lies beyond the observable universe is like trying to decipher a puzzle with only a small portion of the pieces visible. The cosmological principle would be challenged by the existence of vast, unobservable regions where the distribution of matter is completely different. This possibility forces us to think more carefully about the nature of the universe and our place within it. It also reminds us that, despite all we have learned about the cosmos, there is still much more to discover, much of which may be fundamentally unknowable. The realm beyond what we can observe remains a tantalizing mystery. While we have come far in our understanding of the cosmos, the universe holds many secrets that may remain hidden forever, lying just beyond our reach. What other topics would you like videos on? Send us your thoughts in the comments. And if you enjoyed what you saw, please leave a like and subscribe. Thanks for watching.